So welcome back to NCSGS. And for our next talk, we're happy to have Kyler Siegel, who will talk about symplectic capacities, unperturbed curves, and convex toric domains.
Okay, so, well, yeah, first of all, thanks very much for the invitation to speak in this seminar. I remember attending this, I have fond memories of attending this seminar back when I was a PhD student, and it's nice to see some of the familiar faces still attending the seminar. And so this talk, so there'll be sort of two competing narratives for this talk. So the main sort of goal of this talk is to basically define a new sequence of symplectic capacities where the definition is actually surprisingly simple. So it doesn't, in the sense that it doesn't really require any fancy machinery to define them. And then hopefully I want to say a little bit about, computation. So computing these in some examples, and then sort of geometric application. So basically giving some new obstructions to so-called stabilized symplectic embeddings. On the other hand, I want to say at least a little bit about sort of the motivation for this definition I'm going to give, which comes from this sort of so-called higher symplectic capacities, which are basically capacities defined using higher algebraic structures in SFT or maybe Floer theory. So this is sort of part of a much bigger project, and this is kind of, I want to explain at least kind of the motivation for these capacities from this sort of more general picture. But I won't say a whole lot about that story. But I want to at least start by saying a little bit about that as motivation. So let me maybe try to just give an outline of what I want to talk about. So I'll try to start with just a very brief review, just sort of as motivation of these capacities, which I denote by GB and GK. These are defined using structures in symplectic field theory. And then I want to define give this sort of new definition of these capacities I call GK tilde. GK tilde is supposed to be an ersatz for GK, so it's expected to be essentially the same as GK, maybe at least in a nice example. So I mean, I'll give some evidence for that. And then I want to just discuss this GK tilde. So describe some of its basic properties, give some computations. So in some sense, the main result will be a computation of these capacities for some family of examples. And then I'll give at least some sort of sample applications. So to these stabilized symplectic embeddings. And then I'll try to say a little bit about the main computation. So I would say that maybe the most interesting part of the computation is the construction of some curves. So I'll try to explain at least how we construct the curves, and maybe there's other perspectives also on how to see those curves. And okay, finally, if there's any time, I'll try to make a few remarks about sort of beyond the GK tilde. So sort of what ways that you might extend this approach, or sort of what other sort of tools you would need to give sort of stronger applications. Okay, so let me start with this sort of general high level picture. So let X be a Liouville domain of any dimension. And then to X, you're supposed to be able to associate some chain complex, which I'll denote by BCH ln of X. So this is a chain complex where with the generators are given by words of Rabe orbits in the boundary of X. So these are sort of unordered words. Strictly speaking, they have to be good Rabe orbits, but you can sort of ignore that condition. So words of Rabe orbits in the boundary of X. And the generator, sorry, the differential is encoded in terms of, roughly speaking, J-holomorphic curves in the symplectization of the boundary of X, which look like this. So these are sort of asymptotically cylindrical curves a la SFT in the symplectization, which have genus 0 and 1 negative n. And there's more general, I mean, you could try to look at some sort of chain complex that involves more general curves, but what's important about these curves is that these are exactly the ones which are sort of expected to be dimensionally stable. So in other words, if you sort of multiply X with C, these curves are expected to persist. So this is essential for the kind of applications I have in mind, which are for these so-called stabilized symplectic embedding problems. Okay, and then, so this is just a chain complex, and we could take its homology. But now let's consider, I want to consider a small skinny ellipsoid symplectically embedded in X. So E skinny, this is my notation, so it's the same dimension. And this is a small, very skinny ellipsoid. So i.e., so E skinny, you can think of as just, so it's some 2n-dimensional ellipsoid with area factors a1 up to an, and then it's sort of maybe some small scaling. So I'll put an epsilon here. And the skinniness condition is that the first area factor is much less than all the other area factors. Okay, so you can sort of think of the skinny ellipsoid as being like this long cigar. You can always find one of these in X. Just, you can just pick one and living inside of a little Darboux ball. And the key property of the skinny ellipsoid is that it has one Rabe orbit of smallest period, which kind of just goes around the small axis of the ellipsoid. And essentially, it has no other Rabe orbits because, I mean, it does have other Rabe orbits, but they're all sort of so long compared to that orbit that you can essentially just ignore them. Okay, and then, so we have X, our domain of interest, we have the skinny ellipsoid, and now we can look at the symplectic cobordism given by the complement. So we have X minus the skinny ellipsoid. So this is symplectic cobordism, and then by sort of SFT functoriality, we should get a map. So I'll call it phi star from maybe the homology of the chain complex associated to X to the one associated to the skinny ellipsoid. Okay, so we get a map at least on the homology level like that. And as I was just saying, the skinny ellipsoid effectively just has one Rabe orbit, and then there's the iterates of that orbit. And so, and moreover, you can show, just for kind of degree parity reasons, that the differential on this complex is trivial. And so we can really identify this with the symmetric, the sort of symmetric algebra on this short Rabe orbit and its iterates, and I want to view this as kind of a polynomial algebra in infinitely many variables. Okay, so it's sort of a polynomial algebra where T1 corresponds to this short orbit, and then T2 corresponds to the double cover of that orbit, and so on. Okay, and then, so from this, we can define some large family of capacities as follows. So they're going to be indexed by elements of this symmetric, of this sort of infinite polynomial algebra. So pick B, an element of this polynomial algebra. And for any such B, we just put, so GB of X is just by definition the minimal action of an element in this homology group which maps to B under the cobordism map. Okay, and here by action, I mean, so for a word of Rabe orbits, this action is just the sum of the periods of the orbits. And for a linear combination of words of orbits, it's just the maximum over all sum ends. Okay, so again, just by sort of, basic functoriality under cobordism maps, this quantity behaves like a capacity. So, for example, it's a symplectic invariant of X. It's invariant under symplectic morphisms, and it's monotone with respect to symplectic embeddings, equidimensional symplectic embeddings of domains. But in some sense, this definition may be a little bit unwieldy because you have this sort of huge indexing set. So it's a little bit hard to figure out what exactly you want to do with this huge family of capacities. So at least as sort of a first approximation, maybe to kind of understand what's going on, let's make a simplified definition. So let's just define a sequence of capacities indexed by positive integers, and I'll define them as follows. So for k a positive integer, let's define gk of x to be the minimum over gb of x, where b looks like tk plus sort of higher order terms. By the way, there's grading. Everything here is sort of, we could grade everything by Conley-Zender index or some function of Conley-Zender index. So I'm not going to say too much about the grading, but for example, with my indexing convention, the variable tk has grading -2, -2k. So and anyway, the grading sort of goes off in one direction. So and by higher order terms, I mean, e.g., like T5. I mean just higher order in the sense of the degree of a monomial. So like T5 plus T2 squared plus T1 T3 squared. I would call that T5 plus higher order terms. There's probably a better way of saying that, but that's what I mean. And now, okay, so what does this GK mean? I mean, this GK is still, I would say, a little bit hard to parse. I mean, if you haven't seen this definition before, it's a little bit hard to parse what's going on. You have this, big chain complex and this map to the skinny ellipsoid, and then we're taking some infimum. Well, I claim that, or maybe not. Let me say not claim, but let me say there's kind of at least a sort of heuristic interpretation for this GK. So this is not a mathematical fact, but this is just sort of a heuristic interpretation, which is, so GK sort of wants to be the minimum energy of a curve. So we're looking at curves in the symplectic completion of X, and it sort of wants to be the minimum energy of an asymptotically cylindrical curve in the completion of X. So let me call this curve C, which is J holomorphic for some J, genus 0, and it satisfies so-called local tangency constraint. So I'll say what that is in a second, but I denote local tangency constraint by TKP like that. So an order K local tangency constraint. So yeah, so let me explain roughly what is this thing. So here, so this is a local tangency constraint. So it's defined by So you pick, what you do is you pick a local, you pick just sort of a germ of a divisor near some point in X. So pick a kind of local divisor. So just a small piece of a divisor D near some point P. And then we require our curves. So we require our curve C to sort of have intersection multiplicity K with the divisor. So it passes through the point P and it has intersection multiplicity K with the divisor at that point. So I'll just say with the pair DP. Okay, so this is sort of the heuristic interpretation of this GK capacity, but there's many reasons why this is not an accurate statement. I mean, for one thing, the GK as we defined it, it's a homological invariant, right? I mean, at the end of the day, it involves the homology of some chain complex. So for example, we need to require that the collection of Rabe orbits are a cycle with respect to this differential. More precisely, we should really be looking at sort of linear combinations of words of Rabe orbits. And of course, the differential on this thing, it's sort of defined using SFT. So in general, it's going to be defined using abstract perturbations. And so in some ways, there's sort of a lot to unpack in this definition. I mean, the differential might be, counting pseudo-holomorphic buildings. So this is really just a sort of heuristic interpretation of this invariant. But so in particular, let me maybe formulate just sort of to set the goals for the rest of the talk. So maybe formulate two specific questions. So the first question that I think is sort of natural to wonder is do you really need, so let me just say, do we really need sort of full SFT functoriality to define this capacity? In other words, I mean, we're invoking sort of all this SFT functoriality in order to kind of make this definition, but ultimately, sort of, it seems like, the capacity should just be involving J holomorphic curves and, just for some choice of J. So you might ask whether you can sort of take a shortcut and just define, make some direct definition. And then the second question, which I would say is related, is just, given how much there is sort of behind the scenes in this definition, is it possible to actually make computations in some natural examples? So can we actually compute GK for some quote unquote natural examples? And in some sense, I would say that these questions are related because, if you had maybe some more direct geometric way of understanding this capacity, then that might also give you an easier route to kind of computing examples. Okay, and that is indeed what happens. So now let me make the definition of this sort of ersatz capacity GK tilde. And again, I would say this definition is surprisingly simple. I mean, it could have almost been made by Gromov 20 years ago, maybe modulo the SFT compactness theorem. So what we do is pick a local divisor. Just as with the definition of this local tangent constraint, just pick a local divisor D near a point, some chosen point P. And so I'm going to assume X here is a Liouville domain to define the capacity for a Liouville domain. And then let's define GK tilde. Okay, so first of all, now it really is the minimum energy of a curve. Okay, so this is now no longer a heuristic. This is actually the definition. So it's the minimum energy of C, where C is a genus zero, so rational, asymptotically cylindrical J-holomorphic curve in the symplectic completion of X and satisfying this local tangency constraint of order K. And then, so normally, in order to get something which is independent of the choice of J, you do something sort of, you do something homological so that you can sort of argue that you have, things on the level of homology are independent of that choice of J. But instead of doing that, I'm just gonna maximize over all J. So then it's manifestly independent of J. More precisely, the class of J. So this is just the space of all almost complex structures J on the symplectic completion of X, which are admissible in the SFT sense. So it's compatible with the symplectic form, and then it's sort of cylindrical type at infinity, and it should be also just sort of a technical condition is that we ask for it to be integrable near P, and it should preserve D, i.e. D should be J-holomorphic. Okay, so then let me just state sort of a basic result about the properties of this invariant. So basically this is saying, so first of all, this GK tilde behaves like a symplectic capacity. So, and by the way, this is the most of the new results I'm mentioning are based on a paper joint with Dusa McDuff. So first of all, okay, so just some sort of basic properties. So this thing here, it's independent. It's independent of the choice of the local divisor and the point, and as one expects with capacities defined using J-holomorphic curves, it sort of scales like symplectic area. So if you multiply the symplectic form by a constant, then the capacity gets just scaled by the same constant. And it's a non-decreasing sequence. By the way, this property here is actually, it's immediate from this definition if you unpack what the local tangency constraint means, but it's actually, this condition actually wasn't obvious for the GK without the tilde. So, which is why I sort of think it's worth mentioning. And then most importantly, this thing behaves like a symplectic capacity. So if you have a symplectic embedding between Liouville domains of the same dimension, then for each K, the GK tilde of the thing you're embedding is at most the value for the target. So in particular, that implies that it's invariant under symplectomorphisms. And then finally, the kind of most non-trivial property, which is also the most delicate, is stabilization. So ideally, I'd like to say that if you just multiply X with C to the N, that the value doesn't change. So this is what you would like to be true. So this is sort of maybe morally true. But so I don't know how to prove this in general. So we sort of prove this under some slightly technical conditions. So stabilization holds provided that the capacity, the kth capacity of X is carried by what I call a formally perturbation invariant moduli space. So this is sort of a technical condition which is basically designed to guarantee that that you have some moduli space which is sort of robust under one parameter deformations. And so maybe I don't want to get into the exact statement of the definition, but for the purposes of this talk, it's enough to maybe it's enough to mention that this holds for our kind of main class of examples. So this holds for 4-dimensional convex toric domains, which and I'll remind you the definition in a second.
May I ask a very naive question? Is it obvious it's finite?
No, that's a good question. It's not obvious that it's finite. In fact, it's not, I guess, finite in general.
Oh, okay.
Yeah. I mean, there's some, I guess you could find some sort of silly examples where it's not finite, like if you, you take probably something like a punctured torus, then there just are no interesting rational curves just for sort of homological reasons.
I guess maybe in that case I would call it 0, right? Or whatever. I guess, yeah, or whatever. If it is.
I would call it. I would say if there are no such, if no
Okay.
curves, then I think it should be infinity. But
Okay, fine. But if there are curves, it's still not obvious, right, that it's a finite number. That is, because it took the maximum over all j's.
Yeah, that's right. Yeah, it could be the case that there's some j where there's no curves, and then there's some j where there are curves or something like that. So.
Oh, I see. Okay.
Yeah, that's right. But I mean, so at least for the purpose of this talk, it's enough to mention that, like, as long as your x embeds into something where you know everything is finite, then it also has to be finite by monotonicity. So, for example, for these convex toric domains, they all embed into just some huge ball, and then you can just show that the ball has finite capacity. So all of these things also have finite capacities for all k.
Okay.
Well, are you assuming some non-degeneracy condition, the boundary of x?
Yeah. So, yeah, I guess in the paper we define it by, yeah, I think we probably technically you should first assume that x has non-degenerate rate dynamics, and then do some sort of like, and then if it doesn't, then you sort of approximate it by x, which does have non-degenerate dynamics.
Okay, thanks.
Yeah, and of course, I mean, you can also define, like, you could also mimic the definition of ETH capacities and define this for any, like, also for closed symplectic manifold, for example, just by taking a supremum over Liouville domains which embed into it. Yeah. So where was it? Yeah. So I was mentioning the stabilization property. By the way, there's you can be a little bit more precise about this. So actually, you don't have to multiply by the sort of this infinite Cn. So if you multiply by just a ball of area A, for example, then this still holds, provided also that A is at least the value of the capacity on X. So you can be a bit more quantitative about the stabilization, but okay. So now let me, maybe it's already familiar to this audience, but let me just maybe briefly remind you what I mean by convex toric domain. So I guess that's sort of a standard definition. So convex toric domain. So this is just a sort of a special, particularly nice class of sort of domains in C to the n. So it's just something of the form. So it's a domain which I denote like this, which is something which is given by sort of the pre-image under the moment map for Cn of some subdomain in Rn. So here mu is just the moment map for the standard torus action on C to the n. Okay, so in particular, these are domains which have a toric, which have a sort of natural torus action on them. And then, so okay, we could talk about whether this condition is necessary or not, but for a convex toric domain, we assume also some some convexity condition, which is that not only is omega convex, but it sort of convex even after you symmetrize it across the axes. So if you look at a sort of symmetrization of omega around the axes, then so we call that symmetrization omega hat, and then this is still convex and compact. Okay, so for example, I mean, in some sense, I think this discussion is already pretty interesting if you even if we just talk about ellipsoids, which is the special case where omega is a triangle, two-dimensional triangle. Okay, so if this is omega, then x omega is four-dimensional, and it's just the ellipsoid EAB. And then more generally in dimension, at least in dimension 2, where I can actually draw it, it's going to look something like, could look something like that. So that don't necessarily require this boundary segment to be smooth, but you sort of, it's some preimage of some domain omega, which is convex, and it's not allowed to sort of bulge out either. Okay, so and then there's sort of another sort of standard piece of notation. So associated to such a convex toric domain, we can define a kind of a norm, or it's not quite a norm, but it's close enough to a norm for our purposes. So denoted like this. So this is this is kind of norm or function, at least defined by, so the sort of size of V is the maximum, the maximal inner product of V with something in omega. Okay, so this is the kind of dual norm associated to omega. So it's kind of it's sort of roughly the dual of the norm whose unit ball is omega. Okay, so then now I can state the kind of our main sort of computational result. So this is also, again, this is joined with McDuff. So this is just a computation of this GK tilde capacity for four-dimensional convex toric domains. So let X omega 4 be a convex toric domain. Then so it's GK capacity. So it can be written as follows. So it's so we're going to look at convex lattice polygons. So convex polygons in R2, where the vertices are integer lattice points, such that the number of lattice points along the boundary is k plus 1. And then we look for the polygon like that, which has minimum length, where length is measured with respect to this kind of norm. So again, it's not quite a norm because it can take on like negative values, but you can just compute length with respect to it as if it were a norm. Okay, so the kind of geometry of omega enters into this notion, this way that we measure length. And so let me maybe first mention that, so for people, so I know there's some ECH experts in the audience, so then there's sort of I want to compare this to the computation of the kth ECH capacity of X omega 4, and this is known to be actually given by the exact same formula, except that instead of asking for k+1 boundary lattice points, you ask for k+1 lattice points on the boundary and interior, I believe. And so this kind of this difference between the looking at all lattice points versus looking at boundary lattice points is sort of it's closely related to the difference between the ECH index and Fredholm index. And in some sense, it's in some sense that the power of ECH comes from the fact that you can really index. You have this this grading by ECH index rather than Fredholm index. But I want to emphasize that these capacities are defined in any dimension, and in particular, they're stable. So this computation here also immediately gives a computation for higher dimensional domains of the form, x omega cross with a sufficiently large ball, or if you want, just cross with Cn. So as in the stabilization result. Okay, so it's a computation dimension 4, but really you can think of it as computation of some capacities for sort of high dimensional domains, which are sort of long in all of the dimensions except for the first 4. Okay, and that'll be kind of crucial for the main applications, which I'll mention some of in a second. Okay, any questions, by the way, before I move on? So let me also mention, just to maybe put this in a little bit more context, so that there's also, I mean, there's various ways that you can refine this definition. I mean, for example, you can consider higher genus curves. So I'm going to stick to just genus 0 curves, but one kind of simple refinement you can make is you can define this thing called, which I denote by GKL, which is where you only allow curves with at most L positive ends. So you put a restriction on how many positive ends you're allowed to see. So you allow at most L positive ends. So and this is again, this behaves like a capacity. Excuse me. With one caveat, which is that this is it's not monotone anymore under arbitrary symplectic embeddings. It's only monotone under sort of exact symplectic embeddings. And so, in particular, if we, so as a special case of this refinement, if you consider the case where L is equal to 1, so you just allow only one positive end, then you're essentially only looking at planes satisfying tangency constraint, and this is expected to agree with the capacities defined by Gut and Hutchings. So more precisely, this at least in the case of a 4-dimensional convex toric domain, this actually we compute this to be exactly the same as the kth Gut-Hutchings capacity, which in turn, I believe, actually don't know if this is, maybe someone else can tell me if this is a proven theorem now or just expected, but this is also expected to agree with the kth Eklund-Hofer capacity.
I know people who claim to have a paper in progress on this.
Okay, so
I'm not one of the authors, so I don't want to. I shouldn't say who they are in case they are not ready to announce this publicly yet.
I see. I might already. Anyways, just to be safe, we'll put a question mark here, but maybe this will be a theorem at some point. But so I would expect that well, first of all, I would expect, and I don't think it would be maybe too difficult to prove that the first equality holds also in higher dimensions. So Good and Hutchings gave an explicit formula for these capacities in every dimension for convex toric domains. And also, I would probably expect it to hold for at least sort of any kind of reasonable Level domain X of any dimension. So where, okay, put reasonable in quotes because I mean, I don't have a proof that these coincide in general, but in order for it to fail, you'd have to find a Level domain which was pretty sort of bad. You'd have to find a Level domain which sort of, I think, which sort of has terrible Rabe dynamics and cannot be C0 approximated by something with reasonable Rabe dynamics. So, but anyway, at least for four-dimensional convex toric domains, these things agree. Now let me. So okay, but we didn't actually compute. So it would be interesting to try to see whether if you sort of play around with the value of L, whether maybe you get some kind of better embedding instructions than if you just take L to be infinity but just for now, just focusing on this computation, I want to try to make this a bit more concrete. So right now, this is formulated in terms of this sort of, I like this formulation because it's sort of easy to remember. It's like this kind of discrete geometry problem. But you can actually be much more precise about the value of the capacity. So maybe I'll state this as a proposition. So actually, there's relatively few convex polygons which could possibly be a minimizer. Okay, so for a convex toric domain, still four-dimensional, as in the theorem, so the theorem is saying that the kth capacity is given by some sort of the sort of minimal length of the the minimal length of the boundary of a convex polygon where length is measured with respect to this norm determined by omega. And moreover, so the claim is that the sort of minimizing polygon P can be assumed to take one of the following forms. Okay, so let me just tell you what the forms are. Okay, so it could look like that. So this is a quadrilateral where, so these are all, remember, integer lattice polygons, and this has slope 1. Or it could look like this. So this is again a quadrilateral. So the top side has length 1, and this has slope S, which is an integer at least 2. Or it could be sorry, my straight lines are not very straight, but it could be a rectangle where the short side has length 1, or it can be so there's 4 cases. And the last case is just a degenerate rectangle, so just a vertical line. Or it could be the reflections of these about the line y equals minus x. So, okay, the point is, I mean, honestly, I actually don't really have great intuition for this proposition. I mean, we just sort of like brute force, showed that anything else can be, any other polygon can be sort of, you can find a polygon of this form which is sort of smaller, which has smaller perimeter. But and actually, I find it a little bit surprising just because you would think sort of for omega arbitrary, you'd think that, if omega is maybe complicated enough that there, you might have to consider polygons with more sides or something like that. But at any rate, the sort of point of the point of this proposition is that it allows you to then give very explicit formula for the capacity for sort of relatively simple domains. So for example, if omega is a triangle or a quadrilateral, you can just directly write down a sort of a closed formula for the capacity. So maybe let me give maybe a simple example. So okay, here's an example. So how you would sort of extract explicit formula. So omega, this is just sort of a cute example. So omega P is sort of the LP ball in R2 living in the first quadrant. So the set of all points in the first quadrant whose LP norm is at most 1. So P is just some, P is sort of some number which is at least 1 or maybe infinity. And then the statement is, so for P greater than some threshold, which happens to be log 2 over log 4/3, GK tilde of the corresponding convex toric domain is given by the following function. So it's 2 periodic in K. So if K is if K is odd, then it's 1 plus I, and if K is even, then it's given by the qth root of 2 plus I. And there's a similar formula if P is less than that threshold, which is 3 periodic. So for P less than or equal to the threshold. And actually, I don't really have a good intuition for why, but this seems to be kind of a general principle that if your domain is sort of pretty close to a ball, then the capacities are 3 periodic, and sort of as it starts to look more like a cube or a polydisk, they become 2 periodic. And by the way, this is sort of just to give you a picture. This is like omega 1 is actually just the ball, the usual round ball, and then omega P is like something like this, and then omega infinity just gives you the cube. And then so using this kind of principle that you can just use the main theorem or use this proposition to just kind of extract explicit formulas, we are able to do things like just give a formula for the ellipsoid. So which actually the formula is already kind of, formula sort of looks something like this. So it's kind of 3 periodic in when the ellipsoid is close to a ball, and then 2 periodic when the ellipsoid kind of has large aspect ratio. So let me just give sort of one sample application of this. So this is a joint work with Christopher Gardner and Hind. So this is about stabilized embeddings of a ellipsoid into another one. And so for this result, I want to assume that the ellipsoids are integral, and we need to make some assumption on the aspect ratio. So A is at least B plus 1. A and B are integers of opposite parity. And then the statement is that, so, okay, first of all, in that case, we can say exactly when you can squeeze one stabilized ellipsoid into another. So this is sort of a typical thing typical problem is you ask kind of what's the smallest scaling factor C so that I can embed E1A into E1B. And here we've stabilized, so it's a high dimensional problem. So the answer is you can do it if and only if C is at least, so there's some function, so 2A over A plus B minus 1. And moreover, so what's relevant for this talk is that this GK tilde give sharp obstructions in this case. So they spit out exactly the sort of minimal value of C. Okay, so this is kind of, I mean, I should say that so that you're not misled. I mean, this in general, if you just take sort of some 4-dimensional ellipsoid here and some other 4-dimensional ellipsoid here, in general, it's not expected to be true. And in fact, it's provably not true that these capacities give sharp obstructions. But, and this is why, so that I do expect, on the other hand, that this bigger family, this more general family, GB, I do expect these to give sharp obstructions for that kind of embedding problem. And there's a fair amount of evidence that should be true. I don't know whether the general GB has, it seems unlikely to me that there's sort of a simple tilde version of this family in general, but it may be the case that there's sort of, you can probe other information contained in this family of capacities using some similar sort of naive approach. I don't know.
I have a question.
Yeah.
So about this here at the bottom, so here I guess capital N is at least 1.
Yeah, sorry.
Yeah, I seem to remember vaguely Dusa said that this was conjectured to be true for maybe like for any A and B that are not integers, satisfy some inequality or something like that.
There's a more there's a conjecture which is maybe due to Dusa, which is the following. So this is sort of maybe a big motivation for me is the following conjecture. So it's in a slightly more specialized case. So you consider, okay, just to simplify things, you assume that the target is a ball. Although I think we could probably formulate a more general version of this conjecture. So the conjecture is for embeddings like this, and the conjecture is that there's an embedding like this if and only if C. So the optimal embedding is given by C equals 3x over x plus 1, provided that x is at least the golden ratio to the 4th.
Yeah, that might be what I'm remembering. Like, I guess what I'm really asking here is, like, you assumed in your theorem that A and B are integers, and I'm wondering whether you think that really is essential, or if it's just a matter of what you're currently able to compute.
Yeah, that's a good question. So, okay, so for this, this is like in a slightly different regime than this problem. So notice that here B has to be at least 2, I guess. But let's just think about this conjecture for a second. So actually, maybe I'll write this as a remark. So the GK tilde capacities give sharp obstructions. So in particular, they sort of prove the above conjecture for for X. So again, there's some integrality assumption. So X is has to be congruent to 2 mod 3. And in fact, I'm not positive, but I'm pretty sure that this is almost if and only if. So I don't think they give sharp obstructions for any other X. And this is related to the thing I was saying, that somehow the GB capacities, there is, there's I think fairly strong evidence that they should just give sharp obstructions. Actually, if I have time, which I probably won't, but I can tell you exactly what you would need to prove that conjecture. But so the expectation is that the GB, the full family, gives sharp obstructions to this problem for any X. But the GK is somehow the fact that the GK or the GK tilde, the way that we've sort of taken this seemingly innocent simplification. So remember the GK without the tilde was given by sort of looking at just B of the form TK plus higher order term. So maybe it looks like not a big simplification, but it turns out this really throws away a lot of information contained by curves and ellipsoids. So you sort of, by only looking at sort of, I don't have a simple way of saying it, but you're only looking at sort of certain curves of minimal energy, and you're losing a lot of information contained by other local tangency curves. So I think similarly, in this setting, it's probably also true that you exactly get sharp obstructions in these integer cases and no other cases, but I'm not positive about that.
Can I add one thing?
Yep.
Just towards Michael's question. I mean, for example, the theorem is definitely not true in a lot more generality. Like, if you just took arbitrary integers, A and B, and you had this opposite, you drop the condition of them having opposite parity, then it's just not a true statement anymore. I mean, if you look at like the conjecture that Kyler wrote, you fixed B equal to 1, and then your A parameter is sufficiently large. So that there are probably statements like that are true, but some kind of statement like this, there are counterexamples. If you just want to say, if you tried to say, for example, pick two integers A and B, then this is the optimal embedding. It's just not a true statement in that level of generality. So.
Okay, so I guess I also have a question, which is how long should I go for? Or maybe I should just even stop now because it's already 36 after.
I mean, technically, we started late. We're about out of time. You could briefly wrap it up if you have something a little more to say.
Okay. Yeah, I mean, actually, maybe I will then just wrap it up. So maybe I guess I'll just maybe say in words. I mean, I was gonna say a little bit about what goes into this computation, and I would say maybe in my opinion, maybe the more interesting part is to produce the curves which give you sort of an upper bound. So you have to show that there exists some J-alomorphic curve which is sort of realizing, which is sort of giving you an upper bound for this formula. And anyways, we constructed the curves essentially using, so these are just, you're looking for curves satisfying a tangency constraint in a convex toric domain. And we constructed them by sort of, first of all, replacing this so I guess I didn't say, but this local tangency constraint is essentially interchangeable with having a negative end on the skinny ellipsoid. I don't think I explicitly said that, but that was sort of implicit in this discussion where I went from the skinny ellipsoid condition to this local tangency constraint condition here. So, and then at any rate, we construct these curves by basically doing sort of some iteratively obstruction bundle gluing using the Hutchings-Taubes gluing result. So, and yeah, I think with that, maybe I'll end. And yeah, many thanks to everyone for listening.
All right, thank you very much. Are there more questions? Okay, well, I'll ask something. So you were saying you think that the GB will give sharp obstructions to ellipsoid embeddings in 4 dimensions?
To the stabilized 4-dimensional ellipsoid.
Stabilized 4 dimensions. But do you think you can see the unstabilized 4-dimensional ellipsoids with these kinds of capacities?
So I mean, the short answer is no. So I mean, it depends what you mean by this kind of capacity, but with specifically with this GB capacity, so the ones like this, you definitely cannot recover the 4-dimensional obstruction, because these capacities are by design they're dimensionally stable. But you know, there are when you stabilize, there are some embeddings which sort of outcompete 4-dimensional embeddings. So you know, if you could recover the 4-dimensional embeddings, then you would be proving obstructions which are not true in higher dimensions.
Okay, but I think you had some more general kind of capacities which you didn't talk about today, which count other genus 0 curves. Is that right?
Yeah, I mean, for example, and this is not something that we wrote down, but you could take this kind of naive, this sort of Gromov style definition. So this is sort of similar to how Gromov originally defined the width. You could just take this definition and then say, with some tweaks, you could just say allow C to be a higher genus curve, and then I think it could well be the case that it recovers the 4. Then I actually would conjecture that it does recover the 4-dimensional ellipsoid settings. But
I was actually asking about genus 0, but other genus 0 curves, like not just curves with one negative end.
Gotcha. Yeah, that's a good question. So yeah, I don't know. I'm not sure the answer to your question. I mean, so if you tried to adapt this definition, so for example, one naive thing you could do is you could just adapt this definition, but replace this local tangency constraint with just k different generic point, k point constraints. If you do that, I'm pretty sure that the capacity you get is just exactly the same as this one. So just for sort of general reasons, at this crude level, I think it doesn't actually matter if you do tangency constraint or point constraints. And that point constraints thing would be sort of morally the kind of naive approach to doing something with multiple negative ends.
Okay.
But on the other hand, if you do something more general, you allow this sort of full family of capacities, so you really allow sort of all spectral invariants, then it may well be the case that you can see 4-dimensional embeddings, but I'm not sure.
Okay. I've always thought philosophically, and this could be wrong, that the ECH capacities, anything you can prove using the ECH capacities, you really only need genus 0 curves, because it's the genus 0 curves that give you the best inequalities. So I would think that if you have some sort of systematic machinery like you do for making capacities out of genus 0 curves, and it should be able to see everything that ECH capacities see.
Yeah, I mean, yeah, I think I would agree with that intuition. So one of the kind of stumbling blocks is that so for the GB capacities, so I think one kind of obvious question is just, can you compute the full GB capacities for like a 4-dimensional ellipsoid? And this is actually turns out to be a surprisingly subtle problem, because it involves some kind of like relatively subtle enumerative geometry problem. So for example, I have from an earlier work, I have like a recursive formula for the capacities of a four-dimensional convex toric domain, but it's sort of even with that, which is sort of the best I can currently do, it's a little bit hard to like extract concrete information from that. And I would imagine that could be adapted to say if you sort of flip this or what, so maybe, or if you generalize this to have sort of multiple positive and multiple negative ends, I would imagine you could generalize the recursion to that case. And then a natural question is sort of, can you find some other maybe better way to compute that more general family for ellipsoids or something like that? So I think I would expect that they do see these abstractions, but then you get into some interesting questions of sort of how do you compute these things?
Mhm. All right.
I have a question. Maybe you already said this, but there was this heuristic between like a Rabe orbit, a curve landing on a Rabe orbit on a very skinny ellipsoid versus a curve being having a tangency constraint.
Yeah.
So you could imagine there is some kind of degeneration process as you could shrink the Rabe orbit. Do you know if this has been worked out or?
Yeah, I mean so we proved some sort of correspondence between these two constraints. So the way, yeah, you would think that there maybe would be like a direct relationship where you like have this end on a skinny ellipsoid, and then you just sort of like, by some sort of like removable singularities theorem, you can sort of get the tangency constraint. I'm not exactly sure how to make that precise, but so what we did instead is we just, starting out with the sort of tangency constraint curve, what you can do is you can just surround this point by a skinny ellipsoid and then stretch the neck and see what happens. And what happens is actually a little bit funny because so you get some degeneration, and it turns out that the curves that you get in the skinny ellipsoid, which satisfy the tangency constraint, satisfied in a kind of degenerate way. So these curves are actually just all multiple covers of a plane with a sort of maximally branched point at this point. So which do actually satisfy the tangency constraint, but in a kind of disappointingly degenerate way, because they're not actually tangent to the curve, they just have a branch point at the point where it passes through the curve. But at any rate, this does give you the correspondence.
So this is a bijective correspondence between curves in this case, or is that a correspondence in a more strict restrictive sense?
Yeah, it's a bijection on sort of the level of moduli spaces. So if you take some moduli space of curves, the simplest case is just you have some moduli space of sort of closed curves, which is robust in the Gromov-Witten sense and satisfies the tangency constraint, then it's equivalent to sort of looking at curves with end on the skinny ellipsoid. That's sort of cobordism of moduli space.
Okay, I see. Thank you.
Any other questions? Dan, it looks like you're talking. I don't know if you're talking to us, but you're muted.
No, sorry, I was talking to a parent.
Oh, okay. Sorry about that. All right, well, let's thank Kyler again. Well, I guess I had one more question. I'm sorry, I forgot to ask this. Well, you were going to tell us like what's beyond your current technology. You had some part of your talk. You're going to talk about beyond all of this.
Oh yeah, I mean, I suppose I already said some remarks about that, but yeah, okay, I guess so. Two beyond directions for me that are interesting are, yeah, so one is just the sort of I mean, one, so yeah, as I was saying, I don't really know if there's like this tilde approach works for the GB, but at any rate, there's still sort of a lot of open questions about the GB capacity. So it's sort of the current sort of state of affairs is that like yeah, there's sort of this computation of GB capacities for ellipsoid, but it looks like one needs maybe other computational approaches which allow you to, which are kind of are sort of transparent enough to, for example, prove this conjecture. Okay, so maybe one beyond thing is maybe just kind of the GB capacities, computing them and maybe seeing if there's some sort of nice geometric definition like the GK tilde, which kind of extracts part of the GB. And then like you already alluded to in your question, I would say, like, for example, defining the sort of generalized version of this capacity, like the higher genus version, I think are sort of worth exploring, and the more general rational curves also, I think, would probably, I don't know if they would give any applications beyond what's already known in dimension 4, but there's probably a lot of information there that's yet to be explored. So yeah, sorry, that was a bit, I was gonna state some more kind of precise beyond questions, but I think maybe I'll just leave it at this speculation for now. So.
All right, thank you. I guess what I really like about your capacities here is, like, there are capacities like Gromov style definitions, which are easy to define and impossible to compute. And then there are like Floor theory technological capacities, which are hard to define rigorously, but then you can compute them. But yours, you have an easy definition and you can compute them. So that's really great.
Right. I mean, I don't know if they can. Yeah. So it would be interesting to see if you can compute them for anything. I mean, presumably they shouldn't be that hard to compute for like 6-dimensional convex toric domains or something like that. But yeah, there's at least anything where you have some reasonable understanding of holomorphic curves, you have a chance of computing them. So.
Awesome. Okay, I'm going to stop the recording now.